Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Well, hello everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to continue with our discussion on thermodynamics, digging deeper and deeper into the content. Before I go any further, I just want to remind everyone that if you're interested in watching any of my previous episodes on thermodynamics, they are all conveniently compiled into a playlist called Thermodynamics Live Streams. There's a link to it right down there in the description. You are more than welcome to check that out if you are interested. Already got a message in the chat from Angelina. It says hello. Hello, Angelina, and welcome back. All right, so without further ado, I present to you Thermodynamics Volume 4. As always, your feedback is more than welcome and highly, highly appreciated. So please feel free to drop your thoughts in the chat if you're watching this live, and if you're watching this in the form of a video, then please feel free to comment. Whatever feedback, whatever pointers, whatever suggestions, whatever harsh criticisms you may have of this content, I want to hear about it. So, all right. So we're going to start things off by reviewing the content from Volume 3. So Volume 3 was all about, whoops, I moved the wrong thing there. There we go. Volume 3 was all about Gibbs free energy. So Gibbs free energy, very, very important property, and also a very, very useful property, and it's related to entropy, which has been sort of the main focal point of this thermodynamics live streams playlist, right? Entropy, disorder, randomness, second law of thermodynamics. For any spontaneous process, the entropy of the universe increases, and this and that. So Gibbs free energy is just kind of like a derived sort of property that's sort of based on entropy. So we did this big long derivation, and we connected Gibbs free energy to the entropy change of the surroundings, which is, again, the criterion for spontaneity, right? Or really with universe, I kind of messed that up. This should say UNIV. I really need to proofread these things before I go live with them. But anyway, so we sort of derived our way to the formula for delta G, which is delta G is equal to delta H, the change in enthalpy, minus T, the temperature, times delta S, which is the change in entropy. And the nice thing about Gibbs free energy is that you can calculate the change in Gibbs free energy using properties that are only defined relative to the system. So remember, the universe is composed of those two components, the system and the surroundings. The surroundings is literally everything else in the universe. The system is the part of the universe that you're studying. And so delta G is great because it's a criterion for spontaneity that allows us to only focus on the system. And the way that Gibbs free energy is sort of related to the change in entropy of the universe is as follows. This equation down here where we have delta G is equal to minus T delta S. And again, I apologize, that shouldn't say SURR, that should say UNIV for delta S of the universe. So we can see that delta G is indeed a criteria for spontaneity, although the sign of delta G is sort of like flipped compared to entropy, right? So for delta G, a spontaneous process is indicated by a negative value of delta G, not a positive one. So we talked about how to calculate delta G when you are given values of the change in enthalpy, delta H, the change in entropy of the system, delta S, and the temperature. And we saw these different scenarios depending on the sign of delta H and the sign of delta S, what the possible values of delta G could be, whether or not you could have a spontaneous or non-spontaneous process as a result of all of that. So that's what we talked about last week in Volume 3. So tonight what we're going to do is we're going to sort of take that, what we know about delta G, and just kind of push it off to the side just for a moment. We're not going to talk about delta G tonight, but we definitely will in some of the live streams that follow. Tonight, what we're going to talk about is something called standard entropy change for a reaction. The standard entropy change for a reaction, and it's given by the symbol delta S with this little degree sign superscript up here and the subscript RXN for reaction. Standard enthalpy change for a reaction. So there's a couple of main ideas when it comes to standard entropy change for a reaction. One of them is that if you can have a chemical reaction, right, and you want to know whether that chemical reaction is spontaneous or non-spontaneous, or to what degree it's spontaneous or non-spontaneous, wouldn't it be amazing if you could just look some information up in a table and be able to predict the direction of spontaneity just with tabulated entropy values that have already been measured, right? That's a really advantageous position to be in as a chemist, right? You don't even have to, get out the flasks and beakers and stuff. You can just look it up in a table and determine whether or not the reaction's spontaneous. And so this is sort of the value that this standard entropy change for a reaction provides to us. But in order to be able to do that, in order to be able to predict the direction of spontaneity using tabulated values of standard entropy, you need to define what standard conditions are, what a standard state is. And so I do have a couple of videos that talk about that. And before we go any further, let me just go ahead and define standard entropy change for a reaction. So standard entropy change for a reaction is basically just the change in entropy for a reaction in which all of the reactants and products are in their standard states. And so this immediately raises the question, okay, well, what the hell is a standard state, right? And so I do have a couple of videos talking about this. I'm going to assume that you probably haven't seen them, but I do have videos talking about this. One of them is called Standard States and Standard Enthalpy Changes. So back in my thermochemistry playlist, we talked a lot about enthalpy. And then there's another video called Standard Enthalpy of Reaction. Neither of these videos are necessarily a prerequisite to understand what I'm about to show you. I'm going to sort of teach this in a bottom-up sort of fashion as if you know nothing about the topic. But I just wanted to point out that these videos do exist. There's links to them in the description, or at least there's a link to the thermochemistry playlist in the description that has these videos. So I would suggest taking a look at them. I really do think that if you watch those, you'll probably get a better understanding of what a standard state is. So there's that. So let's talk about what a standard state is. Well, it's different depending on what state of matter the substance is in. So for gases, for instance, a standard state of a gas is when you have a pure sample of that gas at a pressure of exactly 1 atmosphere. And for liquids and solids, the standard state is defined as the pure substance in its most stable form at a pressure of 1 atmosphere and at the temperature of interest. Oftentimes, it's going to be reported as 25 degrees Celsius. That's kind of like the most commonly reported temperature in chemistry textbooks. And for anything that's dissolved within a solution, the standard state of that substance is such that the concentration of that substance in solution is exactly 1 molar, right? So this is sort of like the standardized practice to determine what these entropy values will be that allow us to have like an apples to apples comparison. We want to be able to compare two chemical reactions, figure out which one's spontaneous, which one's not. They have to be at sort of the same, they have to be measured to the same standard. And so that's why we have these standard states. So this is one form of the formula for how to calculate delta S reaction, standard delta S for reaction. And it's simply the entropy or the standard entropy of your products minus the standard entropy of your reactants, right? So entropy, remember, is a state function, very similar to enthalpy. Enthalpy is also a state function. And the beautiful thing about state functions is that you can calculate the change of a state function simply by taking the difference between the final state and the initial state. It doesn't depend on the exact path by which you take to get from reactants to products. So we have this equation here. So really all we need to do is to have a way to measure the standard enthalpy of the reactants and the products, and we could quite easily compute the standard entropy change. I hope I don't make that mistake again, the standard entropy change for a reaction. And so how exactly do you measure these things? Well, this leads us into this is like a perfect segue into a discussion on the third law of thermodynamics, right? So if we remember our laws of thermodynamics, right? First law, energy can neither be created nor destroyed. Total energy of the universe is constant. That's the first law. Second law, which we learned a couple of streams ago, is that for any spontaneous process, the entropy of the universe increases. The third law of thermodynamics tells us that the entropy of a perfect crystal at 0 kelvins, which is absolute zero, the coldest possible temperature that exists, is 0. The entropy of a perfect crystal at 0 Kelvin is 0. So if we imagine a perfectly ordered crystal at a temperature of 0 kelvins, well, remember that the formula for entropy, right? The very, very first formula for entropy that we looked up was this one right here. This is the Boltzmann equation. S, the entropy, is equal to K, the Boltzmann constant, times the natural logarithm of W, where W is the number of energetically equivalent ways to arrange the components of the sample. Now, if you have a perfectly ordered crystal at 0 Kelvin, well, W is equal to 1. There's only one possible energetically equivalent way to arrange the components of such a crystal. And so you end up getting S equals K times the natural logarithm of 1. The natural logarithm of 1 is 0, and so S becomes 0. And so the significance of this is that there exists an absolute 0 for entropy, right? Just as there's an absolute 0 for temperature, there's an absolute 0 for entropy. So we don't have to define arbitrarily a 0 value and then measure entropy for everything else relative to that 0. No, there actually exists an absolute 0. And so what I'm going to show you is, you'll bear with me for just a second here. So I'm going to pull up a table here. This is just something that I found online. This shows us what are called standard molar entropies of various different substances, right? So we have carbon in the form of diamond and graphite, silicon, germanium. So these are the standard molar entropies. So when you talk about what these numbers are, these numbers are sort of defined relative to that absolute 0 of entropy that is defined by the third law of thermodynamics. And so anytime you'll be asked to calculate standard entropy of reaction, you'll be using tabulated standard molar entropies for the reactants and products. And so it's as simple as just looking them up and using a formula. We're going to get to that formula in just a few minutes. So these are a bunch of standard molar entropies. Notice that the unit of standard molar entropy is joules per Kelvin per mole. Let me see if I can sort of zoom in on that right here. So the unit, right, is joules over moles times kelvins, right? And so the reason why it's molar entropy, right, is because entropy is an extensive property. Entropy depends on the amount of the sample. And so by using molar entropies, we're talking about how much energy is dispersed in 1 mole of these various substances in their standard states, right? And so somewhere in the back of your chemistry textbook, there's a table that looks very similar to this, where you have your tabulated standard molar entropies for a variety of substances that have been measured by scientists. So, all right, so let's go back to the PowerPoint real quick as we sort of continue this discussion. And so let's talk about some factors that affect the value of standard molar entropy, right? This S with the degree sign up there, right? So what are some factors? There's 5 main factors that affect the value of standard molar entropy. One of them is the state of matter. Another one is molar mass. We have different allotropes whenever that's applicable. We have molecular complexity, how complex the molecule is. And we have the extent of dissolution, right? Whether or not something is dissolved to make a solution, right? So we're going to talk about these factors one by one, and then we're going to finish things off by talking about the actual formula that's used to calculate standard entropy change for a reaction. So let's talk about state of matter real quick. Now, this is something that we've already touched on in a previous live stream, right? The entropy of a gas is greater than the entropy of a liquid, which is greater than the entropy of a solid, right? Gases have way more energetically equivalent ways to arrange the components of a sample of gas than you do for a liquid, than you do for a solid. And so it's no surprise here that if we see here that we have water, right? The standard molar entropy of both liquid water and water vapor, the standard molar entropy of the water vapor, 188.8 joules per mole per Kelvin, much higher than that of liquid water, which is 70.0 joules per mole per Kelvin, right? So again, this is pretty straightforward. We already talked about entropy and state of matter, so we can, I think we can move on. Another factor that influences the value of standard molar entropy is molar mass. So here we have a table that shows 3 metals. These are alkali metals. They're all in the same group, the same vertical column of the periodic table, and so they have similar chemical reactivity, but look at their standard molar entropies, right? The standard molar entropy of potassium, with the largest molar mass of the 3, is larger than the standard molar entropy of sodium, which is larger than the standard molar entropy of lithium. So it seems like the higher your molar mass gets, the greater your value of standard molar entropy, all else the same. Now, the reason for this is pretty complex, but I'll try to briefly explain why standard molar entropy generally increases with increasing molar mass. When you have a larger molar mass, what you have are more electrons, you have greater energy levels, and when the energy levels of those electrons get greater and greater, they also become more closely spaced. And because those energy levels are more closely spaced in those larger atoms, you have a greater extent of energy dispersal and therefore a greater standard molar entropy. So with standard molar entropy, just what we're really talking about is like places to put energy, if you will, the degree of energy dispersal within these substances. So the long story short of it is that the higher your molar mass, the greater your standard molar entropy, all else being equal. So let's go ahead and move on to allotropes. So allotropes are basically just different forms of the same element. So some elements can exist as multiple forms. A classic example of this is carbon, which can exist as diamond, right? So we have the standard molar entropy of diamond, 2.4 joules per mole per Kelvin. And we also have that of graphite, another form, another allotrope of carbon, coming in with a standard molar entropy of 5.7 joules per mole per Kelvin, right? So what is the difference? Why does graphite have more entropy than diamond? Well, if we look at the structures, right, of graphite and of diamond, right? Diamond is a much more like rigid structure, right? Graphite is composed of these like big sheets of hexagons that are sort of fused together. But those sheets of graphite can actually move. They can sort of slide around one another. And so this allows for greater energy dispersal, additional places to put energy, if you will. Whereas the structure of diamond is much more rigid. Those atoms are all pretty much locked into place. Yeah, they do vibrate a little bit, but they don't have nearly the freedom and flexibility to move around and disperse energy than the carbon atoms of graphite do. And so therefore, if I just go back to that slide, it makes sense why graphite has a higher standard molar entropy than diamond does, right? So there's allotropes. We're going to move right on, talk about molecular complexity. So this one is where it starts to get a little bit more interesting. So here we have two substances. We have argon gas and we have nitric oxide gas. That's NO, right? Notice that the molar mass of argon is greater than the molar mass of nitric oxide, but the standard molar entropy of nitric oxide is greater than the standard molar entropy of argon. So a couple of slides ago, we said that higher molar mass means higher standard molar entropy, but there's also an important component to this, which is molecular complexity, right? Nitric oxide has two atoms in it, and argon only has the one. And when you have two atoms connected by a bond, you have more energetically equivalent configurations, right? Because that bond can sort of vibrate around, it can twist, it can rotate. All of those vibrations and translations and rotations and what have yous represent additional places for energy to be dispersed. And so the more complex the molecule is, the higher your standard molar entropy. Standard molar entropy increases with increasing molecular complexity. I've got a couple other messages in the chat. One from Cerelia. It says, hello. Hello, Cerelia. How are you? One from JR8IC. It says, hi, everyone. Hello. Good to have you with us. Thanks for being here. By the way, if anybody would like to support this stream, there's a couple ways to do it. You can give it a thumbs up, not just for my own ego, but because liking is actually sharing. When you give something a thumbs up, it actually sort of promotes the video in the algorithm, and it allows the video to receive more impressions and ideally some more views. So liking is sharing, and so that's why I appreciate leaving likes. It's not just so I can just, salivate over the like count. I really don't give a shit about that, but I do want more people to see it. So that I do care about. Also, if you want to donate via Super Chat or through Streamlabs, sending a Super Chat, that's pretty straightforward. And Streamlabs, there's actually a link down below, so you can actually do like text-to-speech donations and stuff like that, make it appear on the screen, make it fun. All right, so we're going to move on. That's how you support the stream if you would like. So we talked about molecular complexity. There's one more we got to talk about, and that is the extent of dissolution. So this is another factor that has an effect on standard molar entropy. So here we have two substances shown. They're both sodium chloride, but one of them solid sodium chloride, and the other one is sodium chloride in aqueous solution, right? Notice that the aqueous sodium chloride has a higher standard molar entropy than solid sodium chloride, which completely makes sense, right? In solid sodium chloride, you have these alternating sodium and chloride ions that are locked into this rigid crystal structure, and in aqueous sodium chloride, well, you have sodium ions and chloride ions sort of freely floating around in that solution. So there's definitely more randomness, more disorder, more energy dispersal on something that's dissolved in solution than there is something that exists as a solid. Okay, so those are all the factors that affect the value of standard molar entropy for a given substance. I hope we have a better understanding of standard molar entropy now, because we are actually going to use it. So I'm going to show you a formula for how to calculate the standard entropy of reaction for a reaction using tabulated standard molar entropies for the reactants and products. So the formula looks like this. So you might not be familiar with this notation. I'll try to explain it to the best of my ability, and then we're actually going to do a problem, and I think it'll make a lot more sense when we do the problem. But it says that the formula is this, where we have delta S reaction standard is equal to the sum, so that's what this sigma means. It's the sum of the standard molar entropies of the products multiplied by their stoichiometric coefficients within that balanced chemical equation. So this lowercase n sub p, that means the stoichiometric coefficient for the products. So it's the sum of all those standard molar entropies for your products multiplied by their coefficients minus the sum of all of the standard molar entropies for all of those reactants multiplied by their stoichiometric coefficients. So like I said, if this sigma notation confuses you, fear not, because I do believe that once you see this formula being used, once we put this to work, we put it in action, I think it'll make a lot more sense. So, and that's what we're going to do right about now. So this problem says to calculate delta S reaction, the standard entropy change for this reaction, and it gives us the balanced chemical equation here, where we have 2 moles of hydrogen sulfide, H2S, reacting with 3 moles of oxygen, O2, to produce 2 moles of water. And water vapor, by the way, it's gas, not liquid. Very, very important that we pay attention to the state of matter, because it matters, right? The state of matter matters. And we also have on the products 2 moles of sulfur dioxide. So bear with me for just a moment. What I'm going to do is I'm going to grab this problem and I'm going to paste it into the whiteboard so that we can take a stab at solving this bad boy. So let's go to the whiteboard and let's paste the problem in. How's everything so far, guys? Is it pretty straightforward? For some reason, it didn't capture the arrow. Let me try that again, guys. Just a moment. Want to make sure I got my reaction arrow up in there. Let's see. Okay, looks like we're good. Okay, so there's our problem. There's our balanced chemical equation. And we are going to compute the standard entropy of reaction for this reaction. And I need to put my degree sign up here because I guess I didn't copy and paste that, right? Very, very important, because we're talking about standard entropy of reaction, right? And so the first thing that we need to do is we need to look up the tabulated standard molar entropy values of every reactant and every product in this chemical reaction. So hydrogen sulfide, oxygen, gaseous water, water vapor, and sulfur dioxide. We have to look up the standard molar entropy values for these substances. And those are, you can find them. There's an appendix somewhere in the back of your chemistry textbook that has all of this information in it. Now, me, in an attempt to be good and prepared for my live stream, I actually wrote them down ahead of time. And so I will go ahead and just sort of write them down. So I'll make a little table here. So I'll have the standard molar entropy up here, and I'll have just the substance over here. So for hydrogen sulfide, H2S, if you look it up in your textbook, that's going to be 205.8. And again, the unit here is joules per mole per Kelvin, right? So 205.8 for hydrogen sulfide. That, of course, is the gas form of it. For oxygen gas, O2, right? Standard molar entropy of that, according to my chemistry textbook, is 205.2 joules per mole per Kelvin. Then we have water vapor, so we have H2O as a gas. Standard molar entropy of that is 188.8 joules per mole per Kelvin. And again, I found all of these in my chemistry textbook, which is what I would encourage you guys to do if you're ever faced with a problem like this. And then finally, for sulfur dioxide, SO2, which is also a gas, the standard molar entropy value is 248.2 joules over moles times kelvins, right? And so we know the formula and we have all the values. Now it's just a matter of plugging these values into the formula and solving the problem, right? And so according to that formula, right, we're talking about the sum. So I'm going to open up like a bracket here because this is going to be a pretty long-winded problem. It's the sum of the standard molar entropies of all of these products multiplied by their coefficients. And so water, that's one of the products. So it's going to be the coefficient in front of water is 2 times the standard molar entropy of water, which is 188.8. So that's 2 times 188.8 joules per mole per Kelvin, right? And we're going to add that to the same thing for the sulfur dioxide. So the coefficient in front of sulfur dioxide is 2, and that's going to be times the standard molar entropy of sulfur dioxide, which is 248.2, and that's joules per moles per Kelvin, right? So this is the products, right? That's the sum of the standard molar entropies of the products multiplied by their stoichiometric coefficients. And then I'm going to just continue this on the bottom. We're going to subtract from that the same thing for the reactants, right? So our reactants are hydrogen sulfide and oxygen. So for hydrogen sulfide, that's going to be 2, the coefficient in front of that H2S, times the standard molar entropy of H2S, which is 205.8 joules per mole per Kelvin, right? And finally, we'll do the same thing with the oxygen, right? So the coefficient in front of that oxygen is a 3, so that'll be 3 times the standard molar entropy of oxygen, which is 205.2 joules per mole per Kelvin. So now we sort of have our work cut out for us. What I'm going to do is I'm going to enter this entire expression into my scientific calculator, and that should spit out the value that we want, as long as I did my calculations correctly in my calculator. So I would encourage you guys to do the same. If you brought your scientific calculator, I guess you don't even necessarily need a scientific calculator, although it makes it a lot easier to solve this problem. But again, anybody who's watching, I would encourage you to do this problem yourself to make sure we get the same thing, because it's entirely possible that I make a mistake. All right, let me calculate this. So we have 2 times 188.8 plus quantity of 2 times 248.2, that whole thing, minus 2 times 205.8 plus 3 times 205.2, and the value that I got is, so the let me erase this here. So the standard molar entropy, that delta S with a degree sign, Rxn, for this is equal to minus 153.2, and that's joules per mole per Kelvin, right? Minus 153.2 joules per mole per Kelvin. So that's actually pretty cool. Like if I wanted to run this reaction in my laboratory, and I want just to figure out like what the standard molar, or not the standard molar entropy, but the standard entropy change for the reaction would be. Well, it turns out I don't even have to worry about that. I don't even have to run the experiment to measure this. I can just use these tabulated values of standard molar entropy along with this formula that we just learned to sort of calculate it without even, cleaning all my glassware and, getting started with a reaction. So that is it guys. Let me know what you think of this. If anything was confusing, perhaps I blew past it pretty quickly. I don't know. But it's pretty straightforward, right? I mean, all you do is you just look up those standard molar entropies, make sure you're paying attention to the state of matter, because like we said, like liquids are different than solids, are different than gases. So make sure you're paying attention to these states of matter in the chemical equation, and then you just use that formula, right? The standard entropy change for your reaction is the sum of all your standard molar entropies of your products multiplied by their coefficients minus the sum of all of those standard molar entropies for your reactants multiplied by their coefficients. And voila, there you have it. So that is standard entropy change for a reaction. So let's go back to this screen. I didn't mean that music to come in there like that, but I'm gonna have to fix that. I'm doing this like new intro. This guy made me an intro, so I've been using it. I don't know if any of you guys watching right now were watching at the beginning, but yeah. So, all right, guys, that is going to do it for tonight's stream. Thank you very, very much for watching. Really, really appreciate your being in here. Kind of a short stream. Looks like it's only been about 30 minutes, but I guess I blew past it faster than I thought I would. So a couple of messages in the chat. Okay, Angelina says, so this is joules per mole per Kelvin. Yes. And she says, but mole of what? Mole of like reactant and product, right? So if I have like 1 mole of the reactant, and so like the reason why we do per mole is because, again, entropy is an extensive property, right? So the entropy of 100 moles of oxygen is going to be greater than the entropy of 1 mole of oxygen. So dividing by the number of moles there are turns it kind of like from an extensive property to an intensive property, and allows us to directly compare standard. That's what we call them, standard molar entropies. So we're talking about the amount of energy that's dispersed when 1 mole of these substances is formed in its standard state. So I hope that explained it. I really do. But all right, guys, so that is it. Thank you again for being in here. Appreciate it. I know I kind of was like starting the outro already before I started answering Angelina's question. Thank you for your questions. I hope I answered them. If not, you know what to do. You can send me an email. You can DM me on Discord, whatever you want to do. But as far as next week goes, next week is December 19th. I am not sure whether or not I will be streaming because I'm going to be out of town. I'm kind of doing this early celebration of Christmas with my family because I'm actually going to be flying out to Colorado for Christmas this year with my family. So we're going to miss like, the 25th at home. So we're going to do that early. But anyway, thanks again for watching. Lots more new content on the way. Leave me that feedback. And all right, everybody, hope you have had a great weekend, and I hope you are all geared up to have a wonderful, safe, awesome, productive week this week. All right, I'm out. Take care.